Welcome to the last block for today. So the first speaker is Markus Wess, who has done the PhD 4 years ago with Lothar here on waves, and he went to Paris and Patrick Joly group and going more into waves. And here is his latest result on time domain solvers for a wave equation on dual cells. You see a cell and a dual cell, and he will explain more about this construction of parallel dual cells.
Thank you, Joachim. Yes, so Joachim took it all away. This is basically what I'm going to talk about. My plan is to make you understand what this picture actually is and how we use it to solve time domain Maxwell's equations. So, little disclaimer here, I got into this work 2 years ago, roughly. So I'm not as brave as Paul to show a Git commit timeline, because it would look way more messy, I guess. So this is all kind of work in progress, and also similar to Lucy, we are still in the documenting and explaining stuff process. But this is the first attempt on explaining this dual cell method and making the code publicly available. Also, I want to emphasize that the Elsevier publishing company was very cooperative and released our paper 2 days ago, so check it out. So this is, where is it? Here. The recent work, which basically explains most of what's going on here, but only in 2D, and I'm going to try to give you an overview on what's going on in 3D. So what do we actually want to do? We want to solve the time domain Maxwell system. Probably all of you are familiar with it. It's a hyperbolic partial differential equation, and you have your electric and magnetic fields, DH, B, and E, which are coupled via curl operators, and also we have the constitutive relations here, which are the material parameters. So yes, in the end, we're gonna deal with an EH field formulation in weak form, which is written down here. So this is time domain system here in weak form with test functions E prime and H prime. And what I'm going to try to tell you is how to semi-discretize this system. So we're dealing with a spatial discretization here, and then use a method of lines-like approach to do the time discretization. But the time discretization actually is not our focus here, but it's the spatial discretization. Okay. So what we are going to do is we're going to use explicit methods in time. Probably also most of you are familiar with that. Also Philipp and Christoph mentioned some explicit methods here. So why do we use explicit methods, or what is an explicit method? Basically, the main premise is that in each time step you merely have to apply an inverse mass matrix, and not the whole system matrix, including some spatial differential operators, but merely a mass matrix. And then the idea is you can make these mass matrices as convenient as possible. The most convenient matrix being an identity, okay, but the diagonal matrix or a block diagonal matrix. And this can be made very fast, and also the inverse can be assembled really fast. So for time domain Maxwell problems, state of the art in explicit methods basically are these two methods. So FDTD, finite difference time domain method, is probably the most popular method for time domain Maxwell system, and is vastly used in engineering applications. And if you hit Google Scholar, you get many hits on publications on this, and also very many recent publications. And then probably the contender are GG methods, which have been around for approximately the same time, but they are also wildly popular, but not as popular as FDTD. So what are the upsides and downsides of these methods? So FDTD is a finite difference method. You only have low order. You have to do hexahedral grids. And in DG, nicely. You have high order, but you have to choose numerical fluxes, penalty parameters, and you have to deal with these kind of complications. So our approach is somehow in the middle of these methods. So we want to have a high order method, which is explicit, but doesn't have or has the efficiency and the ideas of FDTD, but doesn't have the limitations of having only low order convergence or hexahedral grids. So what is FDTD all about? Basically, it's nothing else than a discrete version of Stokes theorem. Everybody knows Stokes theorem, meaning that you can compute the curl of a function by an integral, a line integral around the boundary of some surface. And since we need curl evaluations in our PDE, we have basically two curls, or we have two such line integrals to compute. And so somehow what I'm trying to convince you here is that naturally a discretization should live on two grids which are somehow interlaced. And this is exactly what FDTD does. FDTD basically has these interlaced hexahedral grids where you approximate your functions, your electric field E and your magnetic field H on these grids, and you approximate point values here and here. So this is what FDTD does. And now the question is, how can we convert this idea to a high-order Galerkin method, which scales nicely and has nice mass matrices? This is basically our goal. So what is the basic idea of the construction? And for this, I'm going to go to 2D again from 3D. So if you think about this gray plane here, then the orange unknowns are basically scalar ones, and the blue ones are vectorial. And these would be the point values in these points would be the unknowns of 2D FDTD simulation somehow. And now you can think of, if you think of point values in these orange dots, you can interpret these as constant or piecewise constant ansatz functions in space. So this degree of freedom here could correspond to a piecewise constant function here on this on these four cells, and the same here. And so if we fiddle around a bit with unknowns and add some more for the vectorial ones, we can do something similar to having these four cells composed into one larger cell for the scalar unknown, for the vectorial unknown. So if we say, okay, the vectorial unknown somehow is a piecewise constant vectorial function here, then piecewise constant in a sense that it's defined on these two cells. Then if you look at these four basis functions, they will all have support in this cell composed, in this large cell composed out of these four smaller cells. So we have these cells here, and we have these cells, and they again define an interlaced Cartesian grid. Still, this is not on tetrahedral grids or triagonal grids what we want to actually use, and still this is not high order. So okay, the only thing I've won by interpreting these basis functions this way is that, okay, we have now not point values but somehow basis functions and can go to a Galerkin setting. So we have these primal elements here on this mesh, and we have these dual elements here on this mesh, and the intersection of them are these what we call cells here. And this is why we call this method cell method, because basically the whole mesh is composed out of these small cells, and out of these cells I can either construct this primal mesh if I join these four smaller cells, or I can construct dual mesh if I join these cells. Okay, and using these cells I may define local high order spaces which should be conforming on each either primal or dual element. So in my case, I took the scalar space as conforming on the primal element and the vectorial space as conforming on the dual element. And then naturally, since these functions are conforming on the elements, but non-conforming over element boundaries, either primal or dual, their derivatives will be distributional. So if we go over to the weak formulation corresponding to these ansatz functions, we get these jump terms here. Okay, and I want to emphasize that we may apply integration by parts here. And we immediately have that what we have here is a formulation which is skew-symmetric. So when we do a discretization and do time stepping, we immediately get energy conservation if we choose conservative time stepping. And if you look at the boundary terms here, we see that we only have to integrate over primal element boundaries, which is convenient for the implementation because we start with our primal mesh and we actually don't want to implement the dual mesh anyway. So yeah.
I missed something. So the orange dots you said is now conforming on the primal mesh?
Yes.
Conforming with respect to?
H1 conforming. So we are in 2D.
So
we're in.
Interpret it as constants?
Yes.
Then you go to the primal mesh and then you say it's conforming?
Yes, because the constant is conforming. And then you can just take this idea to high order and then just define H1 conforming, locally H1 conforming spaces on each primal element, like a standard DG space somehow. Okay, now the only thing that is actually missing is we need to construct the basis, because I just said, okay, we define these spaces. So how do we construct the basis? And we need to go to our to the triagonal or tetrahedral meshes, because this is what we ultimately want to use. Yes.
Should you have the weak formulation? So you have two lines. So one line should be on the primal mesh and one on the dual one.
Well, it somehow is, but okay, since you're conforming, okay, look at the test and ansatz functions. So H is the ansatz function. It's conforming on the primal mesh. So I can here write this duality product here on the primal mesh, and here somehow I shifted this to the test functions, which is also on the primal mesh. So here I merely have to integrate over the primal elements and also over the element boundaries. I can apply integration by parts here, and then I would have here the other boundaries. But due to implementational reasons, we don't want to do that because we don't.
The two forms are the same. What is important for symplectic methods?
Exactly. So if you want to have a symplectic time stepping, then you want to have this skew symmetry here. Okay, so how do we define these discrete spaces? So instead of starting with a hexahedral mesh, we start with a mesh consisting of triangles here. And then to generate the dual mesh, we do barycentric mesh refinement. So we take the barycenter of each triangle and connect it to the midpoints of the sides of the triangle. And then we connect each of those. And so we have this orangish, purplish on the beamer primal element, which consists of these three quadrilaterals. And then here we have this dual element, which consists of 1, 2, 3, 4, 5 quadrilaterals. So each primal element consists of 3 cells, but the dual elements, they can consist of as many cells as this vertex has adjoining triangles. So this is okay. And now we need to define the basis functions, and for this we just map the unit square into each of these quadrilaterals. So we pick nodal basis functions with respect to some nodes, and we map these basis functions into this quadrilateral. And obviously we have to, since we for these, we want to be conforming on this whole primal element. So we have to identify basis functions corresponding to a degree of freedom which lies on this interior boundary here. Keep in mind that this mapping is not affine. There is no affine mapping from the unit square to general quadrilateral here, but it's bilinear at least. So it's not as nice as it could be, but it's still nice enough. Okay, and then actually we're good to go. So in NGSolve, the only thing that is mainly missing are these spaces because, well, they are very non-standard and they are not included. So we had to implement these spaces. And these spaces are implemented in this extra package add-on dual cell spaces, which we can just import. And okay, we can look at our spaces. So the H1 primal cells, we have a mesh with 2 elements, or the one has 7 degrees of freedom per element. Why 7? Okay, if this is 1 element, then we have 1, 2, 3, 4. And then we have here 1, 2, and 1 missing here on the boundary. So these are the number of elements here. We can look at the basis functions. Yes, and you see they are. So you see basically the mesh still consists of the primal elements as we know them, but the basis functions they respect this additional structure of the dual mesh, and you see that. We have kinks on these inner boundaries. Okay, now we need the dual, the space on the dual mesh, and we do the same. We map here the unit square into this quadrilateral, and of course here we need vectorial degrees of freedom, so we get more. And again, if we want to be H-curl conforming, we have to identify the degree of freedom corresponding to the tangential component of this inner edge of the dual cell of the dual element, which is actually an outer edge of the primal. So the mapping is here similar. Again, we can look at these basis functions. Here I picked the lowest order space, so but we can nicely see the support of these basis functions, which respects again our dual elements. Okay, so the support of each of these basis functions is purely in one dual element. Okay. Yes. So.
Does the NGSolve triangulation have just the triangles, or?
Yes, this has just the triangles, but the basis functions are defined in a way that they are 0 in one part of the triangle. The web GUI, okay, the web GUI can do that if you tell the web GUI to use the correct points for drawing. That's the trick here. The refinement?
Yeah.
Okay, so actually we don't do the refinement. That's the whole point of it. We just define the basis functions, which are defined, which have a support on these parts, but we don't actually construct the refined mesh.
Single cost.
So.
You must do it at least on the reference element.
Yes, on the reference element, the only thing I need is the mapping from the unit square to each of the 3 things.
Okay, and for that, to construct that, you actually do not need to have the. Okay.
For this construction, I just need the mapping into the reference element, and then the mapping from the reference element to the physical element is the same as in everything else. Okay, so let's sum up the construction. So we do or do not, as we have heard, we do the barycentric mesh refinement, at least theoretically. We construct the basis function on the reference square, and then the basis functions are transformed to the physical cells. What I left out here is that for the vectorial variables, we have to use polar or covariant transformation, depending on the elements, to get the conforming spaces to preserve the quantities we want to preserve, tangential or normal component. Okay, and we have to identify the correct degrees of freedom on each primal or dual cell. And then the global spaces are just, okay, you embed this by extending it by 0. So in 3D, basically everything works the same. You just have to draw more arrows. You embed your unit cube into this general hexahedron. So we have this hex, and now each tetrahedron consists of 4 hexes. You have this embedding, which is now trilinear, and again you use covariant transformations, and you identify the correct functions. Okay, and pardon? It's unique. Again, the refinement is again you pick the barycenter, and you connect it to the midpoints or to the barycenters of the faces of the tet, which gives you so this construction is unique. Yes. What is not entirely unique is the mapping up to some rotations, but.
Find the correct way to remap. So it's an additional information that you need to add to your mapping. No? Yes.
Yes.
Okay.
Exactly.
It's a Ballinger function, and you pass the Ballinger functions. Okay.
Yeah. Okay. So in 3D, again, we get a similar variational formulation. We have some boundary terms here. In 3D, obviously, looking at basis functions is not as pleasant, but we can count how many degrees of freedom we actually expect to have. And as a small finger exercise, you could recount this and see that this actually does the correct thing. So the number of doves is indeed correct. Okay, so what I left out up until now is I said we construct the basis functions as nodal basis with respect to some nodes. I said some nodes because, well, how do we pick the nodes? The thing is, we want to have efficient mass matrices. So we want to have ideally, we have diagonal or block diagonal mass matrices. And we are free to pick the integration or the points, the nodes, however we like. The only thing that we have to do is we have to pick some on these inner edges to ensure conformity. But other than that, we may pick them however we like. And now the idea is to just pick them as tensor products of some Gauss-Radeau integration rules. So the integration points of the Gauss-Radeau integration rules. And then if we use these integration rules to approximate the mass matrices, so a classical mass lumping approach, we will get, so in the scalar case, we will really get diagonal mass matrices. And in the vectorial case, we have some blocks depending on how many elements meet in one vertex, but independent of the polynomial degree, which is very nice. Okay, let's see how this works. Obviously, we need some integration rules for that, for computing the integrals. This is why we have this function get integration rules, and you can give this guy some order. This gives you some integration rules that integrate all the basis functions up to order 2 correctly. So basically, integration rules that respect the division into these smaller cells. Now, these ones are not the ones used for the construction. These can be used for interpolation or whatever. If you want to have the correct integration rules corresponding to one space, you just use, where is it? Okay, now let's put it like that. Somehow here I'm missing the execution of the notebook. Okay, but the main point is that that we can get the integration rules from the space here. So we have the finite element space here, exactly. And then you just pass these integration rules to the differential symbol. And then what we actually should see here is that we indeed get a diagonal mass matrix, but somehow I messed up the last build of this notebook, so we don't get an output here, so we don't see the sparsity pattern. But you can imagine this is a nice, very nice sparsity pattern here. Okay. Anyway, since I'm low on time, this is good. I don't have to go over this too thoroughly. The point is that this mass lumping, this improves the speed of the the setup and the factorization and the application of the inverse mass matrices vastly. Because for starters, you don't really assemble the mass matrices. You just have to basically assemble them on the fly on each element. The factorization is very simple because either it is diagonal anyway, so you just have to invert one scalar, or it is block diagonal, and we already know the block structure. And we also exploit this fact, so this is an additional matrix class we're using here, which is very, very fast. Also, it's called super sparse because it's even more sparse. Yes. And also, this application of the inverse mass matrices is very nice for parallelization because you can do it element-wise and should also work very well on GPUs to take away your question, probably. But we haven't done this yet, so this is on our to-do list. Okay, now we have the mass matrices. What's missing are the discrete differential operators. And here I have some outputs, which is nice. So for the discrete differential operators, we need the volume term, and we need also these edge integrals. And here we also use a nice trick, which is borrowed from DG methods. Since we have the covariant transformation of the curl basis function, then the curl of these basis functions is kind of a Piola transform, and this cancels out. And so the integral here is actually independent of the geometry. So we can assemble this element matrix once and reuse it. And when I say once, I mean more than once, because there are equivalence classes of elements with respect to rotations. But still, it's a very low number of matrices we actually have to assemble, which makes this very efficient because we don't ever have to assemble a big matrix here. Okay, so to verify that this all works, we may compute the derivative of so the gradient of a Gaussian peak. We can interpolate into our space the Gaussian peak, which looks like a Gaussian peak, which makes me happy. And then we may just apply the discrete gradient and see that this somehow looks like a gradient of a Gaussian, which is good. Okay, now I'm almost out of time, but I want to show some examples. Time stepping, we just use leapfrog, enough said. So we have to apply one of each mass matrices in each time step. Okay, let's look at a simple example here. If we just start with a Gaussian beam, somewhere here should be again a plot, but I think it's still loading, hopefully. If it's not loading, then I have to fire up the notebook as it is. Let's see. Okay, so this is basically all I've told you before. For estimating the CFL condition, we just do a power iteration. There is nothing more necessary than in the actual time stepping. Okay, let's see. Okay. And okay, we get a nice wave propagating forth and back. Okay, this is a very small problem. It has like 160,000 unknowns. And if we look at how many degrees of freedom per second we are able to compute, it's like 130 million degrees of freedom per second, which I think seems impressive, but yeah, people who actually know different codes have to compare that. Okay, now this is a 2D toy problem. Let's see what we can do in 3D. Here here I just also used some toy problem. I used this waveguide here. I put some inclusion, which is a sphere inside here, and then I introduce a wave from this side and propagate it through the waveguide. Now this problem is a bit larger. We have 1.3 million degrees of freedom. We set up the mass matrices. We invert them. You see this not even takes seconds. It's very fast because actually we don't really set up the large matrices. And now the kernel has died. Restart and run all. Let's see if it lets me do it again, or if it dies again. Yes. Okay, here now we should see. I should be starting a wave to propagate here. And I'm plotting every 100 time steps, so each time you see a new plot, there are 100 times 1.3 million degrees of freedom inverted. Okay. Okay, and I think I don't have time to show the last notebook, but there will be a hands-on session. Okay, so Joachim says I have time. Then I also show the last notebook.
Stopped exactly now.
I stopped exactly where it gets interesting. This was, yeah. But
Are you hiding something?
yes, obviously I'm hiding something. This would have been the next crash. Okay, so what we see here is a bit of a more elaborate example, but it's again in 2D. It's the well-known ring resonator experiment. What do we have? We look at two waveguides here, two open waveguides, and a ring-shaped thing here. And as you can see, we have very, very small features in the mesh here. So our CFL condition will actually be terrible. And we need to make very, very small time steps here. And what we're going to do is we're going to propagate the wave from here to here, and it will resonate in this ring, and then it will again jump on this waveguide and propagate in this direction. Okay, since we don't want to impose boundary conditions here, but some absorbing boundaries, we implement PMLs. Time domain PMLs are a bit of a longer story, but in the end you end up with a larger system of kind of damped wave equations, and you get some additional unknowns here. Okay, this was PML in like 2 words. We hit this with a pulse, which has a frequency, so it's more or less a wavelet-like pulse. And let's see whether, okay, here the time loop is already running. We see the wave has started from here. It's propagating here, and it has already jumped over to this ring resonator thing. Here the PML damps it out again, so this wave runs out of the domain without reflections. And if we wait some time, this guy should arrive here, jump over to this wire, and go in this direction. Okay, and while this runs, I'm going to sum up. I presented this nice method. If anybody has more questions, I will be available on Wednesday in the hands-on tutorials. Maybe we can try to build this thing together and run some examples. And with that, I'd like to thank you.
Okay. Thank you, Markus. Next participant ask questions later or send more detail on Wednesday.